Hello, everybody. Welcome to my presentation about supervised learning for biomedical applications. First of all, I would like to thank the organizers for having me. So you may wonder why there is a lot of potential in supervised learning for biomedical applications. And actually, this is something that has increased rather recently for several reasons. One is that there is much more data available. Technological advances have enabled the acquisition and also the processing and the storage of large amounts of data, and also data of different modalities, such as, for example, gene expression or brain physiology, like EEG and fMRI and so on. And so now it has become possible to really acquire very large amounts of data from patients in different conditions. And this is, of course, a huge resource that can be made use of with machine learning methods. And also what is very important is that computer resources have become much stronger, much more performing in the recent past. And this has also, of course, enabled, for example, AI methods. You will have heard recently of ChatGPT and so on. This would not have been possible without a large amount of computational resources that are very performing and that allow to create very complex computational models. And then also what is very important is that people have become, and researchers have become, more literate in other domains. There is an increase in interdisciplinarity. Of course, funding agencies have played a big role here as well. But overall and generally, computer scientists have learned to speak with medical people or clinicians, and the other way around. There are still very big gaps, but at least some common terminology and there is more overlap across domains, which allows and facilitates collaboration, and so this has also led to an increase in research outputs where machine learning, including supervised machine learning, has been used for biomedical applications. Now, I want to just briefly show you some examples where we have used supervised learning for such applications. And so the first one is this paper that we published quite recently, where we investigate the powers of EEG data in order to assist in dementia diagnosis. In particular, we looked at different types of dementia, because this is an important topic. For example, if one wants to prescribe medication, then still it is a big challenge to identify the exact type of dementia. Is it Alzheimer's disease dementia, for example, or Parkinson's disease dementia, and so on. And so the question that we asked is, can we use computational methods in order to facilitate and help with such diagnosis? And to do this, we looked at EEG data. EEG data is very practical because it can be acquired relatively cheaply. So here you see an example where one has such a recording and equipment from EEG, and you can see the person has their eyes closed in this case. But also one can have the eyes open. And this is actually one of the big topics of this particular paper, and I will come to that in a minute. But essentially, the important thing here is that EEG data is very cheap, can be relatively quickly acquired, and there is not major problems like for example, in other ways, in other methods where one looks at brain activity. One has to have, for example, radioactive substances and that are tracers which facilitate or which allow to acquire such information. But with EEG data, this is not necessary, and it's, as I said, very cost efficient. And I cannot go into much detail here, so I just want to briefly summarize what we found. And we found that actually by looking, for example, at the specific case of Alzheimer's disease dementia and dementia with Lewy bodies. So this is the task here was to differentiate between those two different types of dementia. What we found is that contrary to what is done in a standard EEG analysis approaches, is we found that by combining eyes closed and eyes open data, we can actually classify with much higher accuracy than if you would only use eyes closed data, which is predominantly done. And this is interesting because as I said, it is against it is a bit exotic, I would say, and also what is very interesting here is that this is in a way a personalized measure, because we can look for each subject what is their eyes closed and their eyes open EEG signal, and then we can compare those two. And so this goes into the direction of personalized medicine. And here you see this quite visually and also quite strikingly, I would say. Here you can see on the top left plot, you can see healthy control subjects where we plotted the ratio between eyes closed and eyes open signals. And you can see here those bars here are very different, strikingly different than the same bars. So the same ratios between those signals in subjects with Alzheimer's disease dementia or with dementia with Lewy bodies or Parkinson's disease dementia. So it's even without computational analysis tools, one can immediately see that there is a big difference between in the healthy case versus the diseased cases. And so this is, I think, one of the insights that we also gained from using supervised machine learning approaches for dementia type classification is that it can also provide new hypotheses or provide new kinds of ideas that then can help us also potentially better understand disease mechanisms and disease progression. So then the second example that I wanted here to describe to you a bit in more detail is this paper here that we published in 2019, where we did not look at the functional activity, but we looked at the structural information of the brain. So we looked at so-called diffusion tensor imaging data. So this is a type of MRI data where one can measure the movement of water molecules by using this MRI technique called diffusion tensor imaging, or DTI. And in this way, one can actually infer information about, or one can infer fiber tracts in the brain. So these are fiber tracts between regions in the brain. And so we can essentially create a connectivity matrix for each subject using DTI information. And so the question that we asked is, by using those connectivity matrices, where we not only have the source and the origin between individual brain regions, but we also have information about the strength of those connections. So we know how strong two brain regions or areas are connected with one another. We don't know the directionality of those connections. So we don't know if region A projects to region B or region B projects to region A, but we know that there's always a statistical confidence associated with this, but we know with high probability that certain areas are connected with one another and how strongly they are connected with one another. And so there's this, as you can imagine, this can be very valuable information, and also this is again something that we can infer for each patient. And it's a bit more costly than the EEG data that I showed before to acquire, because here you need a scanner, an MRI scanner, which can be quite costly. Nevertheless, it is also non-invasive, and so there are minimal side effects from this. Now, just to better describe the approach that we employed here, so we use data from different databases, from two different databases, the NKI dataset. You can read in the paper in more detail about those two datasets, but essentially we obtained information on healthy subjects from the NKI dataset. And then we also obtain information on healthy subjects as well as subjects with Alzheimer's disease from the ADNI dataset. So we have those two datasets. And then what we did here is that we simulated how the brain connectivity changes during normal aging. So if a person just ages normally without Alzheimer's disease, how do those brain connections change over time? Because we know indeed that there are significant changes actually during normal aging. So we know fairly well which brain regions lose most of their fiber strength connectivity across time. And so what we did is we created a model. Of course, it's a simplified model. Nevertheless, it is a useful model because it allowed us to capture very well how this connectivity matrix changes at each stage. And in this particular work, we can approximate a stage with approximately 1 year. So we can associate it with 1 year of aging, normal time, physical time. And so what we did is we simulated over 15 years or stages how those brain connectivities change for each subject. So given a starting brain connectivity matrix, we then simulated how it changes over time. And then what we did the same thing, but we had pathological aging. So the aging, of course, pathological aging is a very specific expression, but in this case, it would refer to aging if a subject has Alzheimer's disease. And so in the end, what we're interested in is how do those trajectories change over time? Because if we can describe this well, then this would be a very valuable tool to identify subjects that will develop Alzheimer's disease symptoms before the onset of those symptoms, right? And so potentially, or that was our goal, we could use this then to diagnose if someone will get Alzheimer's disease symptoms most likely in the future. And what this allowed us to do is also that we could identify signatures of the brain of people with Alzheimer's disease. So because we had this network approach, and then we could quantify those particular signatures of those networks which associated strongly with Alzheimer's disease type of brain connectivity matrices. So to do this, we used a complex network approach. So we quantified measures of complex networks. This is an entire field in mathematics, and it's a way to capture certain features of complex networks. And the brain is a very complex network, as you of course know. But for example, in the human brain, there are so-called hubs. So these are regions that are strongly connected with other brain regions, much more than you would assume based on a random regular network. And so there are a wide range of different features of such complex networks, including also modularity or centrality. These are all features. And indeed, what we found is that if we then trained a support vector machine as our machine learning tool, then we found that we could, with very high performance, we could classify if a subject had Alzheimer's disease or not, based on those simulated networks. So this is also, I think, noteworthy, is that we simulated the progression of those brain connectivity matrices. So because we did not have the real data at each stage, of course, this would be a huge data set that doesn't exist to the best of my knowledge. And so what we did is, assuming that that this is the true progression profile, then we could actually very well classify the two different states of healthy or Alzheimer's disease after approximately -5 or -4 stages or years. So here you see this statistical measure of the p-value, and again at -5 or -4 years, the p-value of the sensitivity becomes here 0.2, it's below 0.25, but the other measures here are below 0.05, so they're all very good here, except with the specificity, but the accuracy is throughout all this time here, is very very low. And so this indicates that yes, indeed, there are certain signature changes in the brains of people with Alzheimer's disease, most likely before current diagnosis is possible. So it seems that just by looking at the structural connectivity, we should be able to diagnose Alzheimer's disease, and we should be able to do this earlier than what currently is being done. Because currently, usually people have, of course, symptoms and then they go to the doctor, but it may well be that this could be done before the symptoms happen. And so ideally, we would like to, of course, also see this in clinical settings used in the future. And of course, another advantage of this is not only that it's early diagnosis, but it's also that it's computational, objective, and quantifiable. So we get around this often very huge variation across doctors and specialists. They can often disagree, right? They can often say that someone has Alzheimer's disease, and the other doctor might disagree. And with those computational tools, we can create coherent and objective methods and techniques that then can also be statistically evaluated. And what is also very important here is that by using this approach, we could actually create a hypothesis on the brain region that is the source or the origin of the pathology. Because what we did is we simulated the progression of Alzheimer's disease by having a starting point. So we said, okay, this is the starting point of Alzheimer's disease in the brain, for example, the hippocampus or the amygdala or the entorhinal cortex. And then we simulated how it diffuses across the network. And the best results we got was when we started in the hippocampus. Then we had the best match with real Alzheimer's disease brain connectivity matrices after some time. And so this work suggests that Alzheimer's disease may develop in the hippocampus. There is some debate about this currently. And so our work indicates that most likely it is in the hippocampus where we should see the first changes in Alzheimer's disease during progression. Now, another topic that is relevant for machine learning and supervised machine learning with a biomedical application is cancer. And so we have done some first step into this direction. We have not yet created a clinically applicable use case, but we are working in this direction. And I just want to share with you some of these steps. And in this case here is what we simulated is we simulated the progression of a brain cancer, a glioblastoma. And we simulated it in 3 dimensions, how it changes its morphology over time, and also what we expect to see with the oxygen saturation, because the oxygen saturation has a big impact on the progression or the division and proliferation of cancer cells. And what we did in this paper here that was published in 2020, we simulated in a very high performance or very efficient computational approach how the cancer grows over time and how it evolves, and how certain substances also change their concentration both spatially as well as temporally. And then ultimately we would like to use this kind of simulations to predict what is going to happen with the cancer, including when we use certain treatments, for example, radiotherapy or chemotherapy. So how do those cancers change their trajectories if we apply cancer therapy? Because if we can do that, then we could optimize cancer therapy. And of course, supervised machine learning would be very, very important there, because if we know the outcome for sufficiently many subjects, then we can train this optimization tool in a supervised way. And this can then ultimately assist doctors with treatment. Of course, we always need doctors and humans in the loop, but this kind of computational methods could assist and help and render the entire therapy more efficient. So I would like to conclude by summarizing the first part, where I looked into generally machine learning based analysis of various data, including, for instance, EEG data, and that this can also deliver some kind of hypothesis, like, for example, that eyes open and eyes closed information should be considered together and combined together. And of course, then that has then also implications with regards what is going on in the brain when someone has the eyes open and closed. How does that change the activity of individual brain regions and so on? And then also what is important is that this can be personalized. Each subject can have their specific analytic computational tool, because this is very different. People can respond very differently to certain diseases, right? There's always some variation across subjects, and such computational tools can create a personalized approach. And then furthermore, I also want to highlight that we can use mechanistic modeling of how the brain changes or how cancer grows, for instance. And by mechanistic, I mean that we really simulate how the disease spreads, for example, in the brain, in the case of Alzheimer's disease that I showed you, or how the cancer cells proliferate and migrate and so on. And then ideally, if we can collect sufficient data and validate, we would like to use this kind of mechanistic approach for treatment. But of course, this has also many challenges, because we need to have sufficiently large numbers of data sets and we need to have a wide range of subjects that have their individual information associated with those data from different ages, for example. This can have an impact as well. So there is of course significant challenges ahead, but there are also many opportunities thanks to supervised machine learning. And so I would like to just conclude by thanking my collaborators. I could not list all of them here, and I would also like to thank my research lab. They are a very lively team, and I would like to also encourage you to feel free to contact me if you have any questions. And of course, I would also like to thank the funders of this research, which would not, without them, this would not have been possible, of course. And I would like to thank you for your attention.